Hello. In the previous lecture, we defined what is the field of fraction of an integral domain, and we also proved its universal property. Let me quickly recall that for two elements, a and b, of an integral domain capital D, as long as b is non-zero, we defined the fraction a over b to be the equivalence class of the pair a comma b, where the equivalence relation is defined as follows: that a comma b is in the same equivalence class as c comma d if a times d is the same as b times c. And this comes from the intuition that these are supposed to be the same fractions. So if a over b is supposed to be the same fraction as c over d, that happens when a times d is the same as b times c. Based on this intuition, we defined and this equivalence relation. We proved that when D is an integral domain, this is indeed an equivalence relation. And then we defined the equivalence class to be the fraction A over B. Then in a natural way, we define addition and multiplication on the set of all the fractions. And we discussed why it's a field. And then we proved the universal property of field of fractions, which says that first we have a copy of our integral domain inside this field by sending a to the fraction that has a in the numerator and 1 in the denominator. Next, we showed that the field of fractions is the smallest field that has a copy of d in it. Meaning, if you give me a field f with a copy of d, then it has also a copy of the field of fractions of d. To be more precise, if f is a ring homomorphism, an injective ring homomorphism from the integral domain capital D to f, then f tilde that sends the fraction a over b to f of the numerator times inverse of f of the denominator is a well-defined injective ring homomorphism from the field of fractions of D to f. Moreover, the copy of D that goes to the field of fractions and then goes to f, and the copy of D that goes directly into f are the same copies. This is what we discussed in the previous lecture, and this is the universal property of field of fractions. At the end of the previous lecture, I also discussed this 4-step strategy of using the universal property of field of fractions in order to show that the field of fractions of an integral domain D is isomorphic to a given ring F. And the steps are like this. The first step is to show that F is a field. The second step is to give an injective ring homomorphism from integral domain D to F. And then we use the universal property of field of fractions to extend this embedding to an embedding of the field of fractions of D into F. And finally, we show that this f tilde is indeed surjective. In examples, often the first part and the fourth part are the parts that you need to work on. And the second part is often easy. And the third part is automatic out of the universal property of field of fractions. Okay, so let's see how we can use this when we want, and how we can show that the field of fractions of the Gaussian integers. And what are the Gaussian integers? They are numbers of the form a plus bi, where a and b are integers. This ring is called this ring of Gaussian integers. So in this example, we want to show that the field of fractions of Gaussian integers is precisely the ring that consists of elements a plus bi, where a and b are rational numbers. That's Q bracket I. Okay, let's see how we can prove this. We are going to follow these 4 steps, meaning first we are going to show that Q bracket I is a field. Next, we find an injective ring homomorphism from Z bracket I to Q bracket I. This should be obvious what it is. And then we use the universal property of field of fractions. And finally, we show that f tilde is surjective. Okay, let's start with arguing why Q bracket I is a field. This means because we already know that Q bracket I is a subring. This we have seen before. It's a subring of ring of complex numbers. It's enough to show that every non-zero element of Q bracket I is a unit. So we pick a non-zero element, Q bracket Q, a non-zero element of Q bracket I, A plus BI. As a complex number, it has an inverse, and the inverse can be computed using the fact that they can multiply both numerator and denominator by the complex conjugate of A plus BI. Let's point out that because A plus BI is non-zero, its complex conjugate is also non-zero. So it does make sense to multiply both numerator and denominator by A minus BI. Doing so, we can compute the real part and imaginary part, and we end up getting that the real part is A over A squared plus B squared, and the imaginary part is negative B over A squared plus B squared. And both of them are rational numbers as soon as A and B are rational numbers. So altogether, we get that the inverse of A plus BI is also inside the ring Q bracket I, and therefore Q bracket I is a field. So this shows the first step. Next, we are looking for an injective ring homomorphism from Z bracket I to Q bracket I, which is clear. It's just the natural embedding. Sending A plus BI to itself is clearly an injective ring homomorphism. Now, using the universal property of field of fractions, this natural embedding can be extended to an embedding from the field of embedding of the field of fractions of the ring of Gaussian integers to Q bracket I. Here, on purpose, I denoted, instead of using the fraction notation, I used the equivalence class notation in order to avoid possible confusion of fraction inside complex numbers with fractions inside the field of fractions of Z bracket I. So indeed, an element of field of fractions of Z bracket I is an equivalence class. And F tilde of this equivalence class is nothing but F of the first component times inverse of F of the second component. So, and this is what we have over here. So that's our F tilde, and the first isomorph, and the universal property of the field of fractions says that F tilde is indeed an injective ring homomorphism. The last step, the final step, is to show that F tilde is surjective. So we pick an arbitrary element of Q bracket I, and we notice that every such element has a real part that's a rational number and an imaginary part that's a rational number. And we can take a common denominator of these two and end up getting a fraction where the numerator is a Gaussian integer, m plus ni, and the denominator is just an ordinary integer, r. But ordinary integers are also Gaussian integers. So this means I managed to write down every element of Q bracket I as a fraction of some Gaussian integer and another Gaussian integer, which means that F tilde is indeed surjective. So we showed that F tilde is a surjective and injective. Injectivity comes from the universal property of field of fractions. Map from the field of fractions of the Gaussian integers to Q bracket I, and that finishes the proof. You've already seen in the discussion and problem session and that field of fractions of integers is rational numbers, and you can do the same for Z bracket root 2 and Q bracket root 2, do the same for root 3 and so on. And if F is a field, then the field of fractions of F is isomorphic to F. Okay, so these are good exercises. Make sure that you know how to do them. Now, next thing that we want to do is to characterize kernels. How can I distinguish kernels from an arbitrary subset of a ring? In group theory, you've seen the importance of kernels. You've seen isomorphism theorems. And we want to do the same for rings now. And okay, so what are the main properties of kernels? We've already seen that if I give you a ring homomorphism, then kernel of F is, first of all, a subgroup, and therefore it's closed under taking difference. If X and Y belong to the kernel, X minus Y also belongs to the kernel. And more importantly, if X is inside the kernel, then I can multiply it with any other element of the ring, and I'm still inside the kernel. So AX and XA, both of them, doesn't matter from what direction, both of them are inside the kernel. And we will discuss that these are the main properties of kernels. These properties characterize kernels, distinguish them from arbitrary subsets of a ring. And this brings us to the definition of ideals. But before I define ideals formally, I should say that this is not the historical route of how mathematicians got to the definition of ideals. In fact, ideals first were introduced by Dedekind and Kummer when they wanted to study, when they want to answer or solve Fermat's last conjecture. So they wanted to use a kind of factorization property, but not for integers, for more general rings. And the rings that they considered did not have this property, do not have this property that, that every element can be uniquely written as product of primes. But they showed that for those rings, the ideal numbers have this property. That's why they call these things ideal. Later, Noether studied these ideals in more general setting, and she dropped numbers and just used ideal, the word ideal. And she developed ideal theory much more. Okay, so, but I mean, we'll come back to this historical note when we discuss prime ideals and factorization later. For now, let's go back to the definition of ideals. A non-empty subset of a ring A is called an ideal if it has these two main properties, meaning for every X and Y inside I, X minus Y should belong to I. And for every X is inside I and every A inside the ring, XA and AX, both of them should be inside I. In that case, we say I is an ideal, and we write down I triangle A. Notice that please do not get confused with this notation and normal subgroups in groups. A here is not a group, A is a ring. Also, it is an additive group, but here A is a ring. So from the context, you have to understand that you are working with ideals. In this group, in this course, we will be mainly working with rings, so there should not be a confusion. Okay, so the way that we defined it and how we got to this definition, it's not surprising to see the next lemma that if F is a ring homomorphism, then its kernel is an ideal. And that gives us a way of getting lots of ideals. But let's see some concrete examples. So for instance, every ring that I give you, the entire ring is definitely an ideal. It's closed under taking difference. And when I multiply it by every element, I am still inside the same ring. The zeros, the set that consists of only zero, the zero ideal, we call it, is an ideal because when I subtract 0 by 0, I get 0. And when I multiply it by every element, I get 0. So it's an ideal. And the next lemma is actually interesting. It says that if I give you an ideal, then if it has a unit element, then it's the entire ring. Okay, let's see why this is the case. Suppose U is a unit and it is inside my ideal. The critical point is this, that if X is inside an ideal, all the multiples of X are also inside that. When U is in I, all multiples of U are inside I. But I give you an arbitrary element A inside the ring. Can it be a multiple of U? Can I write it as U times something? And the answer is yes, it has a solution. This u times something equals to a has a solution because u is a unit. I can write a as a times u inverse times u. And because u is inside I deduce that a is inside I, therefore I is everything. So again, if I give you an ideal of a ring, if it has a unit, then it's the entire ring. This immediately implies that in a field, the only ideals, there are exactly two ideals, and the only ones are 0 and the entire field. Why is that the case? So take an ideal, let's call it I, and notice that if this ideal is not 0, then it has a non-zero element. Non-zero elements of a field are units. That means this ideal has a unit. But by the previous lemma, that implies that this ideal is the entire ring, the entire field F. So overall, we deduce that when my ring is a field, then from ideal point of view, it's not that rich. It has only two ideals, the 0 ideal and the entire field. Is that it? Do we have the same shape, the same picture for every ring? Of course not. For instance, if I give you the ring of integers, we have already seen that the residue map from ring of integers to ring of integers modulo n is a surjective ring homomorphism, and its kernel kernel is the multiples of n. So kernel of C sub n is nz. Because kernel of any ring homomorphism is an ideal, we deduce that nz is an ideal of Z. Of course, I mean, this is rather easy. One can check it directly, but this is one way of arguing it. So for every positive integer n, let's say, the set for every non-negative integer n, the set of multiples of n form an ideal of ring of integers. But how about an arbitrary ring? Can I construct many ideals? How is the way of constructing it? If I give you a bunch of elements in a ring, can we find the smallest ideal that contains these elements? The answer is yes. This is the way to do it. I'm going to present it only for unital commutative rings, but you can play with it and try to understand what this ideal is when the ring is not either unital or commutative. But for now, and for the majority of this course, we focus on unital commutative rings. So suppose A is a unital commutative ring, x1 xn are elements of this ring. Then what is the smallest ideal of A that contains these elements? The claim is that this ideal consists of A linear combinations of xi's. What does that mean? This means elements of the form a1x1 plus a2x2 anxn such that ai's are inside this ring. We call this the ideal generated by xi's, and we denote it by angle x1 xn angle. So in the Artin's book, parentheses are used, but I prefer to avoid the use of parentheses to avoid the possible confusion with elements of direct product of A sub i's. So we use the angle notation in order to denote this set, the ideal generated by x sub i's. Okay, what do we have to do? We have to show, first of all, this set, let's call it I, is indeed an ideal. Second, we have to show this ideal contains x sub i's. Third, we have to show that every other ideal that contains x sub i's contains I as a subset. So these are the three steps that we have to do. Let's start with the first step. Why is I an ideal? That means we have to pick two elements of this set and show that their difference is inside I. We have to pick one element inside the set and an arbitrary element inside the ring and show that their product is inside I. So let's start with the first step. We pick y and y prime inside I. That means both of them are A linear combinations of x sub i's. That means y is sigma a sub I x sub I, and y prime is a sub I prime x sub I for some coefficients that belong to this ring. And then when we look at y minus y prime, because from additive point of view, it's an abelian group, I can bring the similar terms close to each other. Then the ith term would be this, a sub I xi minus a sub I prime xi. By associativity, I can factor out, by distribution, I can factor out x sub I. And then I get that this element is also an A-linear combination of x1 dot xn, and therefore it is inside I. It shows that I is closed under taking difference. Now we take an element of I and an element of the ring capital A. We look at their product, and we have to argue why AY belongs to I. Because y is inside this I, this means that y can be written as an A-linear combination of x sub i's, which means there are a sub i's inside the ring capital A such that y is sigma a sub I x sub I. We multiply both sides by A, then we use distribution and associativity in order to deduce that it is sigma I from 1 to n of A times A sub I parentheses times x sub I, which means AY is also an A-linear combination of x sub i's, which means it belongs to I. So this shows that I is indeed an ideal of this ring. Now, next we say why I contains x sub i's, and that's rather easy. I have to say why x sub I can be written as a linear combination of x1 dot xn. We pick coefficients 0 for all the terms except x sub I, and for x sub I we pick 1. Then clearly x sub I is written as an a linear combination of x1 dot xn, therefore it belongs to I. The final step is to show that every ideal that contains x1 dot xn has I as a subset, which means we have to pick an arbitrary element of I and argue why this element belongs to J. An arbitrary element of I is an A-linear combination of x1 dot xn, which means it is of the form a1x1, a2x2 dot an xn. I have to say why this element is inside J. But we do know that J is an ideal. We do know that xi's belong to J. That means no matter what a sub i's are, a sub I x sub I belong to J. Now J is closed under addition because it's an ideal. And that means I can add these terms and deduce that their summation is also inside J. And that's exactly what we wanted to show. This implies that I is a subset of J, and therefore, what happened? I is a subset of J, and therefore it's the smallest ideal of A, which contains x sub i's. Now, then we start with a single element, then the ideal generated by this element is called a principal ideal. A principal ideal, in the commutative setting, by the previous lemma, we know that all the elements are multiples of x. So it consists of ax. That's why we sometimes write it as ax or xa. And this notation is consistent with what we used for ring of integers, where we wrote multiples of n by nz. So it's a good exercise to see that when we add all the terms of two ideals, we get a new ideal. And when we take the finite summations of product of pairs of two ideals, we end up getting a new ideal. So these are good exercises, and we will be using these exercises later as well. So I encourage you to to try to show them. Okay, so let's go back to characterization of ideals. What do I mean by that? Kernels I meant. So we started the discussion and definition of ideals by saying that we want to characterize kernels. In order to characterize kernels, we need to define quotient rings. So let's recall from group theory that if I give you an abelian group and any subgroup will be automatically normal, so then we can talk about the quotient group of A by H. What is the set? The underlying set of the quotient group is the set of all the cosets. What is the operation? So when I add the coset represented by X to the coset represented by Y, then the coset that we end up getting is the coset that's represented by X plus Y. So we pick a representative from each one of these cosets and we add these coset representatives. And the whole point was, in the group theory you've seen, that this operation is actually well defined. And at the end, it gives you a group structure on the space and the set of all the cosets. And let me also recall another result from group theory that we are going to use. And the result says that two cosets, X plus H and X prime plus H, are equal precisely when the difference between the coset representatives belong to the subgroup. So if X minus X prime is inside H, this happens precisely when the cosets represented by X and X prime are equal. Okay, now let's go back to ring theory. We are given an ideal I of a ring A. In particular, I is a subgroup of A. And therefore, I can talk about the quotient additive group. So the space of cosets of I inside A with plus forms an abelian group. So in order to make it into a ring, it's enough to define a multiplication on this set. So that's our next goal. We want to define a multiplication on the set of all the cosets of I. What is it? We pick two cosets. One of them is represented by X, the other one is represented by Y. Then I'm going to define the product to be the coset that's represented by XY. So the coset that's represented by XY is defined to be the product of these two cosets. Now, why is it well defined? What does that mean? You see, in this definition, I'm using the choice of representatives X and Y. A priori, it's not clear why if I choose two other representatives, I end up getting the same result. So let's make it an explicit implication. If x1 plus I is the same as x2 plus I, and y1 plus I is the same as y2 plus I, how do I know that x1, y1 plus I is the same coset as x2, y2 plus I? Okay, working with cosets is not that easy. Let's use the implication that we have over here and write the same implications in terms of elements. Saying that x1 plus I is the same as x2 plus I is equivalent to saying that x1 minus x2 is I. And similarly, this next condition is the same as saying y1 minus y2 belongs to I. Now, what we want to conclude is that the difference between x1, y1 and x2, y2 belongs to the ideal I. So that's our target, that's our goal. And the technique that we are going to use is it's a familiar kind of technique. Either you can see it in the proof of the product theorem when you're finding derivative of product of two functions, or when we wanted to show that we can do arithmetic incongruences, congruence arithmetic, when we can do multiplication mod n. The same type of argument had been used there. So what is it? We want to show that x1, y1 minus x2, y2 belongs to I. We are going to introduce this middleman, add it and subtract it. And the middle man is x1, y2. Now notice that the first two terms have an x1 in common. I'm going to factor it out from left. And then the next two terms have a y2 in common, and then factoring it out from right. Now notice that y1 minus y2 belongs to I, and therefore any multiple of it belongs to I. x1 minus x2 belongs to I, and therefore every multiple of this belongs again to I. And I is closed under addition, and that's why we get that x1, y1 minus x2, y2 belongs to I. And that's exactly what we wanted to show. Now it is rather easy to check that this set of cosets with these two operations plus and dot forms a ring. And why is it the case? Okay, we have already discussed that these guys are operations. The only thing that we need to show is why, the ring properties. Why is it, why do we have distribution? Why do we have associativity and so on? But if you think about it, the operations are defined in a way that we can just choose coset representatives and then do the operation. And at the end, we end up getting that because A has these properties, because A is a ring, because A has these properties, we can deduce the same properties for this new set, the set of all the cosets with these operations. I leave it to you to check these properties. These are rather easy, and they don't provide a new insight. So I leave it to you to check. Okay, well, how about the second part? What does the second part says? The second part says that we have a natural map from A to this new ring. By the way, this new ring is called a quotient ring or a factor ring of A. Okay, we have a natural quotient map. So now that we call that ring quotient, this map is also called a quotient map. We have a natural quotient map from A to the quotient ring A over I. And what is it? It just sends A to the coset that's represented by A. Then this map is a surjective ring homomorphism. The map that sends A to the coset that's represented by A is a surjective ring homomorphism. Moreover, kernel of this ring homomorphism is precisely I. So that's the content of this proposition. And I've already said that the first part I'm leaving it for you. Okay, so let's go to the second part. We want to say why piece of I is a ring homomorphism. That means we have to check why it preserves addition and multiplication. Let's start with addition. The multiplication is similar. So we pick x and y. Then piece of I of x is the coset that's represented by x. Piece of I of y is the coset that's represented by y. But summation of these cosets is the coset that's represented by sum of the coset representatives. And that's precisely P sub I of x plus y. That means P sub I is an additive group homomorphism. It preserves addition. Similarly, we can check that it preserves multiplication, as you can see over here. So P sub I is a ring homomorphism. Now, why is it surjective? Because every element of A over I is a coset. It is of the form x plus I, and x plus I means P sub I of x. Therefore, it's surjective. Okay, so it's a surjective ring homomorphism. But what do we know about the kernel of P sub I? X belongs to the kernel of P sub I if and only if P sub I of x is the zero of the codomain, zero of A over I, zero of the quotient ring of A by I. Zero of the quotient ring is the coset that's represented by zero. So this means x belongs to the kernel if and only if x plus I is the same as 0 plus I. But from group theory, we know two cosets are equal if and only if the difference between the coset representatives belong to the subgroup. So x plus I is equal to 0 plus I if and only if x minus 0 belongs to I. And that means x is inside I. So we realize that x is in the kernel of p sub I if and only if it is inside I, which means the kernel of the natural quotient map is I. As an immediate corollary, we deduce the characterization of kernels. We deduce that a subset of a ring is kernel of some ring homomorphism precisely when I is an ideal. Okay, let's quickly go over the logic. Let's go this way. If I is kernel of some ring homomorphism, that means for some ring homomorphism f, I is kernel of f, then we've seen that kernel of f is an ideal. So immediately we get this direction. Now, how about the converse? If I is an ideal, then by the discussion that we just had, it is the kernel of the natural quotient map, P sub I. So it's kernel of some ring homomorphism. Okay, so we get a characterization of kernels. Now, as we promised, we want to get to the first isomorphism theorem. So I want to prove the first isomorphism theorem for rings. But before doing so, let's recall the first isomorphism theorem for groups. So we are given a group homomorphism f from G to G prime. Then the first isomorphism theorem for groups says that the quotient group G modeled by the kernel of f is isomorphic to the image of f. In fact, it gives more detail. It says that the map f bar from the quotient group G modeled by the kernel of f to the image of f, which sends the coset represented by G to what f sends G, is an isomorphism. I mean, there are many layers to this statement. So first of all, why such a map is actually well defined. Second, why is it a group homomorphism? Third, why is it a bijection? Fourth, why is it surjective? I mean, why is it injective? Why is it surjective? So all these steps needed an argument, that you've seen these steps in your group theory course. So now we are going to use this statement and prove a similar statement for rings. Okay, what is the first isomorphism theorem for rings? So suppose F is a ring homomorphism from a ring A to another ring A prime. Then A modeled by the kernel of F is isomorphic to the image of F as rings. So you see the same statement holds not as groups, but rather as rings. And we have more detail. We have the concrete isomorphism between these two rings. What is the isomorphism? The map that sends the coset represented by A to F of A. That's our isomorphism. We can also write it in the diagram form. So we have this function f that goes from A to A prime, but that clearly factors to going to the image and then combining it with the natural embedding of image into A prime. Image of f at the end of the day is a subring of A prime. So on one hand, we have this. Then we have kernel of f. That's an ideal. So we can talk about the factor, the natural quotient map going to A over kernel of f. And what this statement says is that I have an isomorphism from this natural quotient map to the image, so that when I go up and come down, I end up getting the same result as going straight down. Okay, so that's the statement of the first isomorphism theorem. Let's prove it. of course, our starting point would be group theory. We know that F being a ring homomorphism is also an additive group homomorphism. So from group theory, we deduce that the same function F bar is indeed an abelian group isomorphism from A modeled by kernel of F as an abelian group to image of F as an abelian group. So in particular, F bar is bijective and it preserves addition. So the only thing that remains is why F bar preserves multiplication. So if we show F bar preserves multiplication, then we deduce that it's a ring homomorphism, and because F bar is an abelian group isomorphism, it's a bijective map, we deduce that it's a ring isomorphism. So it's enough to focus on multiplication now. This means I have to check why F bar of product of two cosets is F bar of each one multiply. F bar of X plus kernel of F times Y plus kernel of F. When I multiply these two cosets, the way that multiplication of cosets are defined is by multiplying the coset representatives and then looking at corresponding coset. That means I get XY plus kernel of F. And F bar of this coset is defined to be F of XY. But F is a ring homomorphism, and therefore it preserves multiplication. So I end up getting that it is F of X times F of Y. F of X is F bar of X plus kernel of F. And F of Y is F bar of the coset that's represented by Y. So altogether, we deduce that F bar preserves multiplication, and so F bar is a ring homomorphism. Combined with the fact that it's a bijection, we deduce that it's a ring isomorphism. Let's see how we can use the first isomorphism theorem of rings. Let's start with an easy example. Let's show that the quotient ring Z modeled by NZ is isomorphic to the ring of integers modulo n as rings. As groups, you have already seen as rings. The trick is always like this, that the quotient rings are not that easy to work with. But what we do, we focus on the numerator and try to find a nice ring homomorphism from the numerator to either the other side or something that contains the other side. And then we use the first isomorphism theorem. Hopefully the image is precisely the other side and the kernel is precisely the denominator. So that's the usual, the common strategy that we take. In this case, Z sub n reminds us of the residue map. So we have the residue map C sub n from the ring of integers to ring of integers modulo n that sends A to the residue class of A mod n. We have already seen that this is a surjective ring homomorphism, and the kernel of C sub n is precisely the ideal NZ, the set of multiples of n. Therefore, by the first isomorphism theorem for rings, we have that Z modeled by the kernel of the residue map C sub n is isomorphic to the image of C sub n. Kernel of C sub n is NZ, image of C sub n is Z sub n. Image of C sub n is Z sub n. And therefore, Z modeled by NZ is isomorphic to the ring of integers modulo n. Let's see a bit more complicated, more useful, interesting example. So next we want to show that the quotient ring of polynomials with coefficients inside rational numbers modeled by the principal ideal x squared minus 2 is isomorphic to the ring Q bracket root 2. That means the ring that's generated by Q and root 2. So why is that the case? So again, we use the same recipe as before, which means on the side that we have a factor ring, we forget about the denominator. We start with the numerator, and try to find a map from the numerator to some other ring that contains the other side. Hopefully our image is supposed to be the other side, and the kernel will be this one. Okay, now let's look at the other side. It's q bracket root 2. What is this? It reminds us, I mean, we know already that this is precisely the image of the evaluation map at root 2. So we do that. We start with the evaluation map from the ring of polynomials with coefficients inside Q to complex numbers. What is it? It says that I give you a polynomial and then you evaluate it at root 2. So that's the definition of evaluation map at root 2. Now, we have already seen that image of this. Okay, what do we do next? We use the first isomorphism theorem, and it says that the ring of polynomials with coefficients inside Q mod out, or the quotient ring of this guy, by the kernel of evaluation map at root 2 is isomorphic with the image of phi sub root 2. Now, image of phi sub root 2, we've seen this before, that this is the smallest subring of complex numbers that contains Q and root 2, and we denoted this by Q bracket root 2. So we have this equality, and by definition, it is the possible values that polynomials with coefficients inside Q can take when we plug in root 2. And the kernel of this map consists of all the polynomials that have root 2 as a 0. So our steps to do, we need to do are the following steps. We have to show that Q bracket root 2 is precisely a set, meaning we only need polynomials of degree at most 1 in order to get the entire image of this map. And second, the kernel is a principal ideal, and it is generated by the polynomial x squared minus 2. Okay, so let's actually start with the kernel. It's often better to start with the kernel. Okay, so we are looking for polynomials that have root 2 as a 0. One candidate is definitely x squared minus 2. That's how we define root 2 indeed. So when I evaluate x squared minus 2, I end up getting 0. Therefore, it is definitely inside the kernel. Now, our claim is that the ideal generated by this guy is the entire thing. One thing that's obvious is that because x squared minus 2 is inside the kernel, the ideal generated by this is definitely a subset of the kernel, because that's the smallest ideal that contains it. Alternatively, we can say all the multiples of x squared minus 2 are definitely here. Now I pick an arbitrary element inside the kernel, and what I do is I'm going to divide it. I use long division, and I divide this polynomial by x squared minus 2. So I'm dividing f of x by x squared minus 2, and I get a quotient and a remainder. Notice the remainder, when I say it's remainder, it means that the degree of r is strictly less than the degree of x squared minus 2. And saying that q and r are quotients, this means f is q times x squared minus 2 plus r. Now, because degree of r is less than 2, it is definitely of the form bx plus a for some rational numbers a and b. So I'm going to continue this in the next lecture, and we will see why kernel of this map is precisely the principal ideal generated by x squared minus 2, and why the image is consists of is the set of elements that are of the form a plus b root 2. This is part of a grand theorem that we will be proving later on, but for now, this is a kind of baby case, you have to produce more results in order to get the general statement of this type. Goodbye.